All right, how is everyone doing this morning? Good, good. Cool. All right. Does anyone have any questions before we get started? No? All right. You excited about fall break next week? Yeah. Cool. All right. Quick reminder about exams. So they were passed back in recitation this week. If you weren't able to attend recitation, just make sure that you talk to your TA to find out when you can get the exam from them. So yeah, you just got to talk to your TA. They have the exams. They're going to give me the exams that requested a regrade today. So I'll get them today. And then I will try to get them done over the weekend. But you'll definitely have them done by next week. Exam regrades, you'll know that they're done because I will post an announcement, or not an announcement, sorry, a comment is what it's called in Canvas. I'll post a comment on your exam saying what your grade is. So whether your exam grade has increased, decreased, or stayed the same. So once you see that comment on the exam, that's when you know that your exam is ready for pickup, and you'll pick up the regrades from me. So original exams from the TA, regrades come from me. Cool. Does anyone have any questions about that? Dope. Let's continue on with our substitution reactions then. All right, so we left off, we talked about our SN2 reaction. Remind me, how many steps are in an SN2 reaction? 1. How many steps are in an SN1 reaction? 2. Beautiful. So our SN2 reaction was nucleophile attacks as leaving group leaves. It happens all in one step. Our SN1 reaction is where your leaving group leaves and then your nucleophile attacks. So we had to keep in mind that you will always make the most stable carbocation before your nucleophile attacks. So you might have a couple of extra steps in the middle of your SN1 reaction. So that's where we was looking at our hydride shifts. The fact that you can have this rearrangement in order to get to a more stable carbocation. And we said our hydride shifts are really common, that they can happen basically anytime you're just going for a 1 degree separation increase. So just going from secondary, tertiary, yes, that will happen. That's going to happen readily. Our alkyl shifts are less common. So for those in general, you need like a 2 degree separation. So that means that you're going from a secondary to a quaternary. That's basically when it'll happen. Or if you get resonance. Remember, unless you can have resonance, resonance always makes your carbocations extra stable. So resonance is just, yeah, it can always happen with resonance. So when we look at that alkyl shift, that methyl is now on the neighboring carbon, and we can see this change in our electrophilic atom. It's important to note that when you're looking at a product, you can immediately know if you had to do SM1 or SN2 because, well, you can't always immediately know, but you can immediately know if it had to be SN1 because if your nucleophile is attached to a different carbon than where your leaving group was located, that means you had a rearrangement. So then that tells you it had to be SN1, right? Because otherwise you would just have, like if your leaving group was here, then your nucleophile would just attack there. The fact that we're going through carbocation rearrangement and you see that leaving group was there, but your nucleophile ends up here, that means you had to do a rearrangement for your nucleophile to be attached to a different carbon than the one with the leaving group. That immediately tells you it had to be an SN1 because you will never see a rearrangement with SN2 because you don't make a carbocation with SN2. You make a carbocation with SN1. So if you have a theoretical primary carbocation, because we don't actually make primary carbocations, but theoretically if you had a primary, then you could get to that have the alkyl shift if you're quaternary or tertiary. All right, are there any questions about carbocation rearrangements? Remember, it must be that immediately neighboring atoms. It is from this one to the immediate neighbor. We're not going to hop over, like if my carbocation was there, we're not going to go all the way over. It has to be right next door. That's where the shift happens, because it is due to that hyperconjugation, where your group is just leaning over and then it falls. So this is what I was trying to illustrate, that we know that it's SN1 for this particular one. It had to be SN1 because my nucleophile is now on a different carbon than where my leaving group was located. So what is step one of an SN1 reaction? Leaving group leaves. So that's what we're going to do first. Step one, leaving group leaves. So I get this secondary carbocation. You must always stop when you see a carbocation. Check to see if you can get a more stable carbocation through your hydride shift or alkyl shift. So you got to look next door to see if you can get something more stable. So right now, it is secondary. I know it's secondary because there are 2 carbons attached. If I moved it here, my carbocation would be primary. That's going to be less stable. So we're definitely not going to move in that direction. But here it is quaternary, so I could have an alkyl shift. So, and because that can happen, it will happen, because you must make the most stable carbocation first. Bless you. So we're going to get that alkyl shift. So that now I have one methyl attached to carbon 2 and the other methyl attached to carbon 3. Now my nucleophile can attack. Now that chloride can attack. Always watch out for carbocation rearrangements with SN1 reactions. Cool. So how it can happen with a primary leaving group. This is way less common. Sorry, I'll keep it in frame. It's very less common. We're only going to do this if I need to rationalize the product formed. Essentially, you are given that product and said, predict a mechanism. Well, then you got to find a way to make it, right? We're not going to predict this product, because what we're going to talk about is how we would predict our products. That's what's up next, in which case then we would have predicted it would be SN2, because this is going to be a primary leaving group. So you wouldn't normally predict this to be an SN1. You would only do this mechanism if you were told that you had to get the rearrangement. So then knowing that I have to find a way to do it, then I know that it had to be SN1, right? So this would be like a minor product, and you're just trying to rationalize what you observe. Okay. Oops. You wouldn't write this as your major product. Like if this was a predict the product, that's not the product that you would draw. That's what I'm trying to emphasize. This is just if you're told to make this product and you got to think about how, then we're going to think about how we can have a concerted alkyl shift with our leaving group leaving. So first, alcohols are bad leaving groups. So we need to protonate it first. Or you could think about it as we have a strong acid. Strong acid is going to protonate something, right? So first step is going to be activation of that alcohol, activation of our leaving group to make that oxonium ion. And remember, since this is acid-base, you need to have that equilibrium arrow on this step. Bronsted acid-base equals you need equilibrium. All right. So now I have an exceptional leaving group on a primary carbon. We will not make primary carbocations. Primary carbocations are extremely unstable. So instead, we can do this alkyl shift, which is good. We needed to have this carbon over here. I no longer have a quaternary carbon. So I know there had to be an alkyl shift, right? So the way to rationalize it, because I can't make a primary carbocation, is to show that the alkyl shift is occurring as that leaving group is leaving. That gives us now a tertiary carbocation. That carbocation we can draw. So now that bromide, which I forgot to draw over here, sorry. That bromide can now attack to give us our desired product. So this is that example of a primary leaving group with a quaternary carbon next door, how you can end up with that alkyl shift to get to a tertiary carbocation. But again, this wouldn't be your major product. This isn't the product that you would draw if you're predicting a product. This is only how you would draw the mechanism to rationalize the fact that you saw a rearrangement. So how do you get a rearrangement without being able to draw a primary carbocation? You show it happening in one step. Cool. All right. The last aspect of our SM1 and SN2 discussion is that we can control it with solvent. So this is a minor factor. We're predominantly going to control our reactions by looking at our nucleophile and our substrate. Those are the primary two factors. But sometimes it'll be hard to tell, and then we will consider solvent as a third factor. So solvent is going to be the last thing that we consider, but it can be used to control a reaction. Right? So it's the last factor to consider, but it can be used to control a reaction mechanism. So in general, your SM1 reactions prefer polar protic solvents, and your SN2 reactions prefer polar aprotic solvents. Polar is just because it dissolves your molecules. That's basically the only reason why polar helps. So it's the protic is SN1, aprotic, not protic, is SN2. So our protic solvents, if we remember, because we talked about that solvent shell that we had when we were looking at our nucleophile strengths, our protic solvents are going to be where you have that hydrogen attached to an electronegative atom. Commonly, we're going to see it with nitrogen and oxygen, but it also works with sulfur. So like all of our sulfur equivalents, so like your thiols, all of those are also protic solvents. So it's anything that's capable of doing hydrogen bonding, or anytime you get that delta positive hydrogen. That's what makes it protic. This is going to favor our cationic intermediates. The way that I always like to remember this is that, like, if you have a lot of protons, you have a lot of H pluses, you already have positive charges, and so then it's going to be that there are counter ions to stabilize those positive charges. So then it's going to help stabilize the positive charge on a carbon as well, right? So like if you have a positive charge in one place, you can have positive charges in other places too, is kind of the gist. So if you see that you get a delta positive hydrogen, it's going to stabilize the carbocation. And the reason why is because you're usually going to have some sort of anionic electronegative atom that can help donate in to stabilize your negative charge, is ultimately why the protic solvents help, or to help stabilize the positive charge, yeah. Sorry, I misspoke there. For our aprotic solvents, these are going to be where you don't have a hydrogen on an electronegative atom. It's essentially just not protic. It's just everything else. So it can't do any sort of hydrogen bonding interaction. These favor our SN2 reactions because your aprotic solvents don't form the tight solvent shells. So because the aprotic solvents don't form the tight solvent shells, that means that it's not going to weaken our nucleophile. So if it doesn't weaken our nucleophile, that means I have a stronger nucleophile, and SN2 is the reaction that cares about the strong nucleophile, right? So that's what we're seeing. Solvent shells are really common with our protic solvents. That means the solvent surrounds the nucleophile. That weakens the nucleophile. SN1 doesn't care about the strength of our nucleophile. But SN2 does. So having a protic solvent with SN2 is typically disfavored because remember, in SN2, your nucleophile has to attack at the same time as the leaving group leaves. So you need it to be really reactive. You need a strong nucleophile. It's in the rate determining step. You need it to be able to react right away. So if you're forming a shell, this like protective bubble around your nucleophile, that's going to slow it down. That's going to disfavor SN2 because it's going to slow down the SN2 reaction because it slows down your nucleophile. So now your nucleophile is all protected and it can't actually get to the electrophile. So now it's going to be a slower reaction. So that's why the protic solvents are disfavored with SN2, usually. Again, this is just a last factor that we consider. There are going to be so many exceptions. This is just a general trend that we can use when we're stuck, right? There'll be a lot of exceptions. So don't start with solvent. Solvent will be the last factor that we consider. All right, so examples of our aprotic solvents. We have DMSO, dimethyl sulfoxide. So if we remember from our exam, in the extra credit, it asked us what a sulfoxide looks like. It's that ketone where sulfur replaces the carbon. So that's what the sulfoxide is. So DMSO, common aprotic solvent. I don't have any hydrogens on electronegative atoms. All of my hydrogens are on carbon. It's not electronegative. They have very similar electronegativities, so they are nonpolar bonds. So there are no delta positive hydrogens on DMSO. DMF is dimethylformamide. So that's where you have this amide, but you have a hydrogen next to the carbonyl. The dimethyl is talking about the two methyls coming off the nitrogen. So that's DMF. Again, no hydrogens on electronegative atoms. All of our hydrogens are on carbon, so there are no delta positive hydrogens. So it's aprotic, not protic. Acetonitrile is where you have that nitrile, the carbon-nitrogen triple bond, and a methyl group on the end. So again, all of the hydrogens on carbon, so it is not protic. Another really common aprotic solvent that I didn't write in is acetone. It is actually 2-propanone, or propan-2-one. Is another very common aprotic solvent. So if you're in lab, you probably use acetone to dissolve any sort of molecules. It's usually like your last wash of your glassware. It's a really good solvent. It's good at dissolving things. Let's think. Yeah, those are all the really common ones. You can have ethyl acetate. So that's an ester. Again, not the IUPAC naming for it, but because it should be ethyl, what would it be? Ethyl ethanoate. Acetate's the common name. These are all good aprotic solvents. Anytime you see hydrogen not on electronegative atom, it's aprotic. And SN2 likes that because these are not going to weaken your nucleophiles. All right. Any questions about anything? Cool. All right. So let's summarize this. Let's make sure that we actually remember everything that we've said so far. So our SN2 reaction, the substrates that it likes are the methyl substrate, the primary, and the secondary. We said that it does not happen for tertiary. And SN2, we'll remember, is one step. And you get that backside attack, which we'll talk about in the stereochemistry part. SN1 is our two steps, and remember that we get carbocations. So the substrates that are favored for SN1 are going to be those secondary and tertiary because they stabilize the positive charge. They stabilize that carbocation. The reason that SN2 substrates were favored were because of sterics, or lack of steric hindrance. SN2 needed a good leaving group because the leaving group is one of the factors in our rate determining step. It's on the substrate. SN1 needs a great leaving group. It needs a great leaving group because that is the only thing involved in our SN1 rate determining step. So the substrate and the quality of the leaving group, those are the only two things we are considering in our speed of our SN1 reaction. So you need a really good leaving group so that it can happen more readily. Our stereochemistry for our SN2, we said that we saw inversion, and that was because of that backside attack. It was accessing that sigma star. For SN1, we saw racemization. And that was because that carbocation is planar. Right, so you could attack from either side. So you got a mixture of front face attack and back face attack. You got a mixture of the wedge and the dash. So you'd have racemization anytime you make that carbocation. It destroyed our stereochemistry. For our nucleophiles, SN2 needs a strong nucleophile. SN1 doesn't care, so we'll usually see a weak nucleophile. But it doesn't care about the strength. So the reason that this strong nucleophile is going to favor SN2 is because if you're a strong nucleophile, that means you're really reactive. You're not going to just wait around for a carbocation to form. You're going to react. You want to go. You're a higher energy. You are just ready to attack right away. So if you're a strong nucleophile, you're just going to go in that first step. So you're going to happen all at once. So the strong nucleophiles will want SN2 because they're going to be really reactive, so they're just going to want to react. SN1 doesn't care because the nucleophile isn't in the rate determining step. For our solvent, our SN2 reaction favors that polar aprotic. Our SN1 reaction favors polar protic. And again, it's because of, for SN2, it's because the protic solvents form a strong solvent shell. Actually, let's write it that way. So because protic solvents form solvent shell that weaken the nucleophile. And again, SM1 doesn't care because SM1 doesn't care about its strength of its nucleophile. It'll typically favor protic because the protic will help stabilize that carbocation a little bit, and it doesn't care about the strength of the nucleophile. So for SN1, having that protic solvent does help stabilize our carbocation, and it doesn't care, SN1 does not care about the strength of the nucleophile. So it doesn't care that your protic solvent is forming the solvent shell, weakening your nucleophile. All right. So if you know that you are doing substitution, then it's usually easiest to look at the substrate first. When you don't know that you're doing substitution or not, it's going to be easier to look at the nucleophile first. So if you know you're doing substitution, then we're going to do substrate, nucleophile, then solvent. If you don't know, meaning we're going to be looking at substitution versus elimination, then we're going to switch that and do nucleophile, then substrate, then solvent. It'll just make it easier. But if you know if you're just trying to pick SM1 versus SN2, it'll be a lot faster to just separate the substrates. So we're going to look at this, and we're going to go, all right, for this substrate, is that going to be primary, secondary, tertiary? Secondary. So this is ultimately going to be our leaving group. We have a strong acid, so it's going to protonate the alcohol. So this is going to become our leaving group. That is secondary. So I have a secondary leaving group. So that tells me nothing, basically. That's saying I'm doing either SM1 or SN2. Because both of them work on a secondary, right? When we look at our substrate, secondary is there on both of them. So that doesn't really help us. So then we look at our nucleophile, and we see our nucleophile is going to be that methanol, right? So that's going to be our nucleophile. That is a weak nucleophile because it is that neutral oxygen. Right? So if there's no negative charge, then it's going to be a neutral nucleophile or a weak nucleophile. So that tells me that it's most likely SN1. And then we can check our solvent and see that our solvent is also methanol. So this is technically going to be what's known as savolysis. That's just where your solvent is also a nucleophile. So you're going to have a solvent breaking a bond is the savolysis. It's a solvent lysis. Lysis means to break. Yeah. Yeah, so I knew the nucleophile was going to be the methanol. My main thing that I'm using to differentiate these is I'm using the hint of the general location, where typically your substrate is going to be to the left of the arrow. And then usually your reagents, meaning the nucleophile, is going to be above the arrow or on the arrow. So that's our first indicator of why it's the nucleophile. How I know it's the solvent is because methanol is one of those protic solvents. It is one of our common solvents. All of our alcohols are also solvents. So we just need to remember that it can be both. So I know it's a nucleophile because it has lone pairs of electrons. And then I know it's a solvent because it was one of the protic solvents that we listed. Essentially, all a solvent is anything that's cheap. It's basically our differentiator. So methanol is a really cheap solvent, really cheap molecule. So we're like, cool. It's a good thing to just dissolve stuff in. But it's protic. So that reinforces the fact that, yeah, we're definitely doing SN1. Right. So if I'm doing SN1, that means that I'm going to have my leaving group leave. I'm going to check to see if I can do any sort of rearrangements. I'm not going to have a more stable carbocation formed anywhere else. So in my mind, I'm imagining this goes away. I get a positive charge. So then I'm like, all right, so that's where my methanol will attack. So that means I'm going to get my OMe attached to that carbon. So then the last thing to consider is that the stereochemistry of it. Remember that with SN1, you're going to have that inversion, or sorry, not inversion, your racemization of your stereochemistry, where you get both inversion and retention. So you can either show it as a straight line, because the line means 50% wedge, 50% dash, or you can show it where you actually draw in the 50% wedge and 50% dash. Or you'll sometimes see it written where you get this squiggly line. That squiggle means 50% wedge, 50% dash. All the squiggle is recognizing like, hey, I know this is a chiral center. I know that this is creating stereochemistry, and I recognize that it's going to be racemized. That's all that squiggle means. It's just another convention that you can use. So all three of these would be correct answers. Either doing this one, these, or this. All three of those are correct answers. If you showed just one wedge or just one dash, if you only did one of these, then that would be incorrect. It's both, because we get racemization with SN1. Right? Does that process make sense? Are you kind of draw those conclusions? Okay. All right, try to do the next one then. You're going to try to predict the reaction, your reagent, and what conditions you need. Conditions meaning solvent. So you have to write an appropriate solvent for this reaction. Whenever you think you have an answer, go ahead and talk to people around you and see if you can agree. All right, so I'm seeing a lot of hesitation. So to do this type of question, you need to ask yourself first, what mechanism do I need? Is it going to be SN1 or SN2? Because that's how we know then what type of nucleophile or type of solvent we need. So you have to first figure out which mechanism it is. And so we're going to use our stereochemistry as our clue. Then, or any sort of attachments, like location changes. Then you're going to figure out what elements do I need? Because whatever elements you see in the product had to come from somewhere. So those are going to be in your nucleophile. So that's going to tell you what your nucleophile had to be. And then you want to think of, all right, what are actual solvents or nucleophiles that align with that desired mechanism? Okay. Try to answer those questions. All right. Still not seeing a lot of talking. So I'm gonna try to get an anonymous poll going to see how we're doing. Because I don't know if it's just because it's Monday and we're tired or what. So go ahead and join, or what, I don't even know what day it is. Oh my gosh. It's Friday. Thank God it's not Monday. All right, it's Friday and we're just done with the week. So go ahead and join Top Hat. Go to tophat.com, log in with Ohio State University, use the SSO, don't use the bypass. And then you will enter in, this is our join code, so that's the course code that you will use. This attendance means literally nothing. All this is so that I know that you are now actually in the Top Hat. It's just so that I know that you were able to join. Yeah, seems about right. We're probably at about 40% attendance. All right. I'm gonna close the attendance. It doesn't matter. If you didn't enter it, it means literally nothing. So don't worry. I'm not even gonna check it. I don't care. So I'm gonna close it. Don't freak out. It means literally nothing. Okay. This is what I want you to do though. Tell me what the mechanism is. Did that reaction have to be SN1 or SN2? Okay. See how we're doing. Okay. All right. So the majority of you are correct. So it is SN2. So if you chose SN2, explain to those around you, and make sure you're all in agreement why. If you did SN1, try to now see why this had to be SN2, now that you know the right answer. All right, does anyone want to tell me why they know it's SN2? Yeah. Yeah, we see inversion of stereochemistry. So that's our indicator, right? I see my wedge went to a dash. I don't see racemization, I see inversion of stereochemistry. That's how I know it had to be SN2, right? So that's how I answer that first question. The next question is, what elements do I need? So what is different? What is changed between my reactant and my product? What elements do you have? Yeah. Yeah, we switched out the functional group. So we went from OTS to CN, right? We went from that tosylate to a nitrile. So we need to lose this thing, and we need to gain this thing. So that means that the elements that I need to have in my nucleophile are going to be a carbon and a nitrogen. So I need to make sure that when I'm picking my nucleophile, it at the very least contains a carbon and a nitrogen. It's the bare minimum it's got to have. I need to have that carbon and that nitrogen. All right, so now we're going to think about what our nucleophile and solvents are that are preferred with an SN2 reaction. So SN2, what kind of nucleophile does it like to have? Strong or weak? Strong. What makes a strong nucleophile? What makes a strong base? Charge, right? Like that negative charge, having electrons. Remember that our bases and our nucleophiles have very similar trends. So I'm going to want an anion. I want a negative charge. The negative charge is what is going to give me a strong nucleophile. SN2, it has to happen all at once, so I need that strong nucleophile. All right, what kind of solvent does SN2 like? Aprotic. So I need an aprotic solvent. So now I got to think about, all right, how do I make this real? So what real reagent, molecule, thing, has carbon and nitrogen and a negative charge? Yeah. So you could do HCN. Is that anionic though? Does that have a negative charge? So if you deprotonate it, then it would. So what could I do to not even have the hydrogen? What could I add instead? Yeah. So if you do ACN, watch out, that's our aprotic solvent. So you can use that as your aprotic solvent. But that's not going to have that negative charge. What kind of compounds have formal charges, the negative charge? Ions, right? Like anionic is an ion. How do I know if it's an anion or an ionic compound? What tells me I have an ionic compound? Metal and a nonmetal. So I have nonmetals, right? Carbon, nitrogen, they're nonmetals. So what kind of metal could I add to make this a real thing? Sodium, yeah, love it. So HCN technically would work if you added a base, but make it even easier on yourself, add the metal, add sodium, so that right away it is now ionic. So now I have NaCN, and you would just pick any aprotic solvent. So someone already said acetonitrile, so we're gonna, cool. You just pick your favorite. Whichever aprotic solvent's your favorite, do that one. They're all equally good. Also, if you don't like sodium, you want to do potassium, cool, that's also a thing. You can pick your favorite metal too. As long as you have that carbon, that nitrogen, the negative charge, then you're all a real thing. That is going to be your good nucleophile. All right. Does that process make sense? Do we want to do more practice? Yeah, okay. It's 10:02, okay. Let's do, oh, I almost gave you the reagent, oops. We'll vote again in Top Hat. Did I close Top Hat? So you can change your answer in Top Hat. Or keep it the same if you think it's still SN2. You can pick whichever one you think is right. All right, for the sake of time, because I just realized it's 10:04, I'm gonna go ahead and close it. So, well, I guess there are only 10 seconds. Well, we're out of time anyway. Okay. So, excellent, good. I'm glad you guys changed it. You all changed it. So it is SN1. Our indicators are the fact that the leaving group and the nucleophile are attached to two different carbons, and I see racemization. That together tells me SN1. I need to have a OME, and I want a weak nucleophile, because SM1 usually prefers weak nucleophiles. So something like methanol, and then if you want to make it really go, you could add some acid if you want to do that, or you could add heat. But technically, you could just write methanol, and I would accept that. Cool. All right, have a wonderful day. Yep.
Your other example.